And we are on.
Excellent. Well, good morning, everybody. I am really glad to be back. I spent an amazing 2 weeks in Russia, and I've had a lot of fun writing all about the adventure of being there. But I know that statistics education is important, so we are back. I want to note that I've structured the last 3 or 4 sessions, I haven't made up my mind yet, a little bit differently than the first 8. So the first 8 were really canonical topics you just have to discuss anytime statistics comes up. But the topics I'm going to be addressing over the next 3 or 4 lectures are things that are quite specific to the biological kinds of problems we deal with. So I know that today is going to be about principal components analysis, or PCA, a technique that lots of people use in biology, but not a lot understand, unfortunately. And we'll probably have a discussion of clustering. We will certainly have a discussion about multiple testing correction, which is probably my favorite beast of the field. And at some point, we're going to have to talk about power calculations, because somebody at some point in your life is going to ask you, why did you do 3 replicates rather than 5? And you best have a good answer for that one. So we'll try to talk through all of those subjects. That's just 4 more sessions, though. And of course, as the news changes from day to day, we'll keep abreast of that, and if we need to change schedule, we'll change schedule. Okay? So let me see, would you mind pulling the door for me? I don't want to have too much extraneous noise here. Okay, so today we're going to talk about PCA, but I wanted to point out that PCA is just one example of these methods that we call dimensionality reduction. So we're going to cover why dimensionality reduction is important in molecular biology, and from there we'll kind of work our way into what PCA itself does. Now you should have access to a shared folder on my Google Drive that gives you all of these slides. And if you're watching from home, I want to tell you, you can also get those slides. Just look at the description of this YouTube video, and in there you'll find a link to that folder. The camera is going to be on me, but the slides are there for everyone to work with. You can print them off or do whatever you want with those. Okay, so let's move ahead. We're going to start with why we need dimensionality reduction. It's always a good question to ask, what purpose does this serve? What need was this intended to fill? And dimensionality reduction is a very big one that a lot of people need. We'll work our way through principal component analysis because it is kind of the standard method in this space. There are other methods, for example, T-SNE, T-SNE, that have been used particularly for visualizing complex data sets. We won't be discussing those. We won't be talking about singular value decomposition or principal factor analysis and so on. These are all relatives, but today we're just going to focus on the great granddaddy of them all, the principal components analysis. And finally, because he had an awful lot to do with the creation of PCA, we're going to talk about Harold Hotelling. That's not a gerund, that's his last name, Hotelling. Who created some of the key statistics that we use in econometrics and other fields. Okay, on we go. So, why bother? Dimensionality reduction matters to us because we often think of biological data as a long table. Okay? So imagine that each column is some sample, and you've measured a whole bunch of different properties for each one. Does anyone work with microarrays or RNA-seq? Microarrays or RNA-seq? Okay. Does anyone work with proteomics? A person or two. Has anyone ever measured more than a dozen different scores for each sample? Yeah. This is something that we do. A lot of the data we produce generate a lot of information about an individual sample. And in all of these cases, we tend to think of them as tables. A column for every sample, a row for every different analyte we're measuring. So if I were taking the example of a microarray, I would have a different row for every transcript that we were measuring for this sample, and a column for every sample. So in those cells, we would write what's the abundance of each of these transcripts. So those are great, but we have a bit of a problem when we have far more rows than we have columns for making our assessments. So if, for example, you have 2 cohorts, say, cases and controls, and you want to know which proteins are changing between these 2, you're going to have problems if you've only got 3 replicates of cases and 3 replicates of controls and 1,000 different proteins for which you have measurements. So dimensionality reduction is one of the things that can help us reduce this vast complexity to a much smaller number of key factors. Okay, so now I want to talk about this n-dimensional space thing. And this is the part where a lot of values just glaze right over, so fight it just as hard as you can. This is an important concept. If you were measuring 3 different properties of every student in this class, height, age, and calories consumed each day. Now, I would put my calories consumed each day above almost anyone because I love jelly beans, right? So I don't look like a big, hefty person, but I tell you, for calories consumed every day, I'm just way up there. So we could imagine then that we have these 3 axes. We said it was age, height, did I say? And calories consumed. So imagine in 3 space, every person in this room fits in here somewhere. So the taller people are higher up on the, say, the y-axis. The people who eat more are way out here on the z-axis. And on the x-axis, we have, did I say height? No, age, right, yes. So you can imagine then that what we end up with is a cloud of points in this 3-dimensional space where each student has some address in that 3-dimensional space. Everyone good so far? Great. All right. So in effect, what we're doing is using the metrics we've evaluated for each sample, each person in this room, as an address, as the coordinates where this person fits in this 3-dimensional space. Okay? All good so far for 3 dimensions. The same principles apply when you're working in 4 dimensions, 4 measurements for each sample, or 5 dimensions, or 1,000 dimensions. So anytime someone starts talking about n-dimensional space, don't immediately glaze over. Just think about as many dimensions as you really can. And our brains are pretty good at working with 3-dimensional space. Everything else just sort of builds on that. Okay, so when we have a very large number of dimensions, our methods for working with the data tend to break down. Dimensionality reduction helps us to beat some of the problems that arise in that case. All right, so do we have too many measurements? Different measurements may be redundant from each other. Now, I've given 2 terms here. We've already talked about correlation. I hope everyone remembers that from a couple months ago. Mutual information is another term that we use for this. It's kind of an information science idea that these 2 values have shared information that where one factor is causing variation, linked variation in 2 metrics. So that's a problem. When we have these different factors all at play, we may find that we have mutual information or correlation hidden among them. So I talked about this case where we may be measuring transcription of different genes, but if those genes are affected by the same transcription factor, you would expect a positive correlation in the measurements of those transcripts. Does everyone see that? Because the same underlying cause here, the transcription factor, is affecting multiple transcripts, multiple genes to be expressed. All right, so that's one example. Now, the next is that we frequently talk about physical metrics. I've mentioned this problem of, we talked about height, for example, and age, and so on. So imagine that you are measuring the size, the physical dimensions, the length, the width, the depth for a sample, and you're also measuring the weight. Generally speaking, we would expect that something, if, for example, you're measuring a leaf length and width, that one correlates with the other, that longer leaves are also wider. Everyone get that? Okay. So physical dimensions also tend to correlate in this way, and we want to be able to deal with that. Okay. So why is it a problem that we see these linkages among our underlying data? First off, I want to give the example that we're trying to make a classifier. Has everyone heard the term classifier? Not necessarily. Okay, that's cool. So I have a bunch of data for cases and controls. I want to say, what things can I measure about a patient that most powerfully separate the cases from the controls. So now I have a training set. I have a bunch of data where a physician has gone through and said this person does have the disease, this person does not have the disease, and I've got measurements for all of them. From that I learn a classifier. That classifier in turn, when given a new patient's measurements, helps to decide whether that person belongs in the cases or the controls category. That's a classifier. So let's imagine that I'm measuring 1,000 genes for every person. If I ask which genes individually are the best for telling a case from a control, I'm going to get back a list. If I then say, okay, these 5 genes were the best individually for discerning whether someone was a case or control, so if I put these 5 together, I'm going to get a much better ability to separate cases from controls. Everyone see where I'm going with this? What if these genes are highly correlated to each other? For example, sharing the same transcription factor. Now I have a redundant signal. I might find that combining these 5 individual genes to make one 5-gene classifier doesn't actually improve my discrimination at all. That's because these genes have a lot of mutual information or a lot of correlation among them. And I want to pick genes that give me different information that makes me build a better classifier. So just combining together individuals isn't really going to help me all that much if they're highly correlated. Okay, so that's one problem. Next, multiple testing correction. We haven't hit this topic, but we were slated to do it this week, but I thought about, was I ready to do a really good punch on that one, and I didn't feel like I was. I'm going to do that one, I think, next week instead. Multiple testing correction is a very, very big deal. It is necessary when we perform a very large number of individual statistical tests. Like if you do 1,000 t-tests, you're going to have some number of false positives that derive from the fact that you've run it a lot of times. Okay, so we'll talk about that soon. But multiple testing is a problem because we have so many different entities, so many different measurements that we have to compare. Okay, so principal component analysis is one of the earliest approaches that came together for this. Probably the first person to do something that we would today think of as PCA is R.A. Fisher. We've mentioned R.A. Fisher in connection with ANOVA and a million other things for that matter. PCA is another one of his brainchildren, but it didn't really get the name PCA and the development of PCA until a later person that we're going to talk about at the end of this lecture, Hotelling. So, why do we call it principal component analysis? Principal, you will note, is spelled with an A-L, not L-E. It's like a principal investigator is always spelled with P-A-L, not C-I-P-L-E, right? That's because a principle is an idea. Principal, with an A-L, means the main ones, right? So principal component analysis is going to prioritize components that it computes. These components are a new representation of your data. If you feed your data 12 measurements for every sample, you're going to get back 12 components. But they're going to be sorted, and they're going to be uncorrelated as well. So this is, we're going to go through this in a little bit more detail and try to talk about how this can be done. But I want you to know that PCA is called that for a very good reason. It's producing components from the metrics that you feed it. Those components will not be correlated with each other meaningfully, and that's important. And it's going to prioritize those components based on which ones are best at explaining the variance in your data. Okay? That in a nutshell is the key thing I would like you to take away from today. You have some number of measurements that come in, you have the same number of components that come out, but now they've been prioritized in terms of the amount of variance they explain. Alright, we will try to unfold that slide by slide. So here we're going to come back to our three-dimensional representation of our data. Everyone remember we were talking about, I still remember, the age, the height, and the number of calories consumed. These three metrics, however, could be anything. I just want you to imagine that all of our data are living in some cloud in three-dimensional space. Now, the data do not all fall at the same address, at the same coordinate location within that three-dimensional space, do they? We see that they're separating quite a lot. Now, they don't separate cleanly on one metric, right? It could be that we see that all of the data have the same x and y coordinates, but they have different z components. That's one possibility. So if all of the variation is happening in one metric, you're not going to see a whole lot of emphasis placed on the other two metrics for telling how the data distribute. But sometimes we see that the data actually distribute as a function of multiple metrics. So here we see that the data are mostly along this line, but there's also variation coming back this way. So we have a way to visualize all of these data, and we can ask sort of what is the long axis of this cloud of data points. Does everyone see that? The long axis? That is to say, if looking at the data themselves, we can create new directions for... I'm going to try this again. The data here are showing up in an x, y, and z axis, and that gives them some sort of shape in this 3D space. We're now going to come up with new axes based on where the data are that does the best job of separating them. So in this little cloud of data, we see that the long axis, the axis over which we see the most variability, stretches from back here to up here. So we now throw away what x, y, and z looked like before, and we define a new axis that is a function of those three variables. We started with an x, y, and z. Now we're going to create something new that we call a, b, and c. So these new axes are chosen so that the variability is best explained at each step without creating a correlation among the components that we're creating. So essentially we look for where we've got this long point. We say this is going to be our new first component. And then we ask, how can we draw in a second component that's orthogonal, not correlated to the first one, that accounts for the second most amount of variance. And then we build a third one that's orthogonal to those two coordinates. So we started with x, y, and z. Now we have the three components that we use as the new addresses for each data point. That's kind of the mind-bending part of this. I'm certainly not going to ask you to write the algorithm that does this for an assignment. This is how these algorithms work, and the most efficient means for producing components from these original metrics are a little complex. All right, on we go. So, what does that look like once it has taken place? One of the things you'll want to evaluate when you have run a principal components analysis is to understand how the original metrics get combined to create the new components. So each component is going to have a form that looks like this. We had our original variables, say x, y, and z, and w, or whatever. And then those original metrics got multiplied by something, some value, that was associated with that axis for computing this component. So those weights are represented right here. The original variables are the v's, and these w's are weights that get assigned to each of the components. This is a linear combination of equations, of variables. We've seen this before in linear modeling, right? So we can say y is a function of x by multiplying it by some weight and adding some constant value. In the same way, when you have multiple variables that you're combining together, you can apply a certain weight to each one, and from that compute a component value. So lots of people are going to ask you when you're looking at a PCA plot down the line, well, this data point didn't look like it clustered with those before. Why does it do so now? To understand how the old metrics relate to the components means figuring out what these weights are on each variable. And PCA will give you that information. All right. So one of the one of the most basic kinds of plots that we see for our principal component analysis is called a screeplot. Remember that principal components analysis is going to prioritize some of these metrics over the others. The assumption in principal component analysis is that the first principal component explains the most variability in the data set. The second component explains the second most variability in the data set. The third component explains the third most variability, and so on down the list. If you give it 12 metrics, it's going to produce 12 components for you. And one of the really trippy things, I think, is that if you've generated a principal components analysis from this data table, if you are given the component values for a sample, you can deduce what the original data were for it. So this is a commutable space that we started with our x, y, and z coordinates. Now we have a, b, and c components. We can get back the original x, y, and z components, though, given the component values. Odd but true. All right, so however, the whole point of this was dimensionality reduction. We wanted to have fewer components to explain our data than we fed it. If we gave it 12 dimensions, we would kind of like to see 2 or 3, probably, that help us to disentangle all of our data. So a screeplot is very good for understanding that. So in the example here, we see that the very first component accounts for upwards of 60% of the variability. The second component contributes another 20% to our understanding of variability. And by the time you get to the third dimension, the third component, you've got very little explanatory value. So understanding how much of the overall variability is explained by these components tells you how many you need to pay attention to in modeling these data. So we're going to see some examples in which the number of components is much larger than the number of the number of metrics is much larger than the number of components you actually need to keep. Okay, so there are a lot of different rules of thumb on how many components you should keep when you're working with principal component analysis. I've given a link to a paper here by Kangalosi and Gareli that is useful in this area, but I will use kind of my arbitrary computer science background on how to do this. The first question I always ask from principal components analysis is how many different components do I need to use to account for at least 50% of the overall variability? Right? That might be just one. It might be just one metric, as in this case, is already enough to explain 50% of your variability. And after that, I add another half of what remains. That gets me to 3/4. How many components do I need to explain 3/4 of my variability? And if I add half of what's left, I can ask how many components do I need to explain 7/8 of my variability? So you can think of this then as each time I'm going to be adding some explanatory power by adding more components. But how rapidly am I getting to a more complete depiction of where all the variability is coming from? Okay, on we go. So we're going to be working with this data set in just a few minutes, but I think I've mentioned the IRIS set to you. IRIS is one of the data sets that's very frequently, that really frequently appears in demonstrations of multivariate analysis. Today we'll use it for this purpose. So we have 3 different IRIS species, and we've measured 4 different metrics for each of them. Plus we have a label on those data points to say which of the 3 species do they come from, the Virginica, the versicolor, and Setosa. Here they've all been colored, and we see 2 different principal components being used to plot these. So I want you to remember how we got here. In this case, we had 4 measurements for each plant, so a 4D space. We produced a principal component analysis of that, and that produced 4 components. We looked at how much variability was accounted for by each of those 4 components, but in the end we visualized using 2 components. This kind of plot is ridiculously common in principal components analysis. You'll walk through a poster hall and you'll see PCA, 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 and almost all of them use this kind of 2D plotting strategy. Does that mean that two components are all you need to explain variability in your data? No, it does not. And I want to try and explain why. You are looking at a projection in 2 dimensions of 4-dimensional data. All right? So, do we know that these 2 circles in yellow right next to each other are right next to each other in 4-dimensional space? We do not. So if I had the pointer here, I'll just point with the water bottle of fate here. So imagine that all of these data lie in a plane, in the plane of the screen here. But this one point is actually out here. We're only seeing 2 dimensions for this data set. And just because something appears to be together in 2 dimensions does not mean it's together in 4. That's why we need to check whether the 3rd dimension is also providing meaningful information, that the 3rd component is also producing meaningful information. If the 3rd component accounts for a large degree of variability, if they're all, one is 40%, one is 38%, one is 36%, a plot like this can be very deceptive. So I want you to be aware that when you use PCA, you really do need to check how much variability you've accounted for. Okay, move forward. This brings us to Harold Hotelling. So I've noted him as a major statistician, an economist, and a traveler. And I have to say, as somebody who chose to uproot his career and move to another continent, I have serious respect for other people who've attempted this. So Harold Hotelling is a great example of that. So probably the metric that is most strongly associated with him is the Hotelling t-squared metric. Hotelling t-squared is a statistic that allows you to combine together a whole bunch of different values. Where we most frequently see this is quality control. So I want you to imagine that we have a mass spectrometer that has been in operation over a space of months. And every week we run a quality control sample on it, and we measure things like how mass accurate is it? How many tandem mass spectra does it produce? What is the range of intensity values that we're seeing? A whole bunch of these. And now we want to say, is the instrument today in good operating order? Because somebody has just shown up with a pile of samples and he wants them run right away, but they're really precious, and if the instrument is in bad shape, I don't want to run them. I want to get everything fixed before this instrument starts working with precious samples. So the Hotelling t-squared metric is able to combine together data from a whole bunch of different metrics that we have computed and allow us to see whether the instrument is performing in different shape today than it was, say, a month ago. Okay, so Hotelling t-squared is valuable for that. Now I mentioned that R.A. Fisher kicked off this world of principal components analysis, but it actually got its name and a whole bunch of subsequent development from Harold Hotelling. So that's brilliant news. After World War II, he was a veteran, served in World War I, had done a whole bunch of other things. He'd been working at Stanford University, I believe in economics. But University of North Carolina made this big decision right in the aftermath of World War II that creating a whole department just in the space of statistics would be really valuable. And they picked Harold Hotelling as their first chair in 1946. He's very much a revered figure at UNC because of that. So he really represented this really key understanding that statistics is not just bad mathematics. It is its own field and it has its own problems to work with. And a lot of his initial work in organizing and recruiting some brilliant talent to UNC made that happen. So the other thing is that he's really a key figure in econometrics. Now I know that we don't live in Gauteng, but we do occasionally make use of toll resources. So has anyone tried to go up to Worcester along the N1? You got to have the right change, right? You don't want to show up there with a 100 Rand bill, right? You want to have your proper change and so on to pay exact change as you go through. So how do you decide as a government what the appropriate amount to charge for that tunnel through the mountains? Do you say, all right, well, we paid 30, what was that?
Just some package.
Oh, some second. Okay, so he wants it free. Am I right? You want it to be free. Okay, but the government paid a lot of money. How many billions did that cost?
I'm sure we've paid it.
Okay, so you're raising the key issue here, right? The resource was expensive.
Yes.
Citizens tend to think, well, I've already paid for it because I paid for the government, therefore why should I be charged to use it? And yet there's this tragedy of the commons thing that shows up. Tragedy of the commons is an economic concept, which is to say that if you have a shared resource and there's no cost for using it, people tend to overuse it. You mean you wouldn't like using that tunnel if it had huge grooves down the concrete, would you? Or down the asphalt? Wouldn't be so great. So hoteling spent an awful lot of time focusing on deciding how the government should proceed in paying for bridges and paying for toll roads and tunnels and things like that. So it's actually an area of very great interest. Econometrics kind of grew out of that. He was one of the first presidents of the Econometric Society. Okay, but I want to point to where this gentleman lived in the course of his life. First off, how many United States citizens do you think have a passport? Is it all of them? You born and you immediately receive a passport in the mail? Not even close. Americans don't like leaving the United States as a rule. So, and some of them actually look at my career suspiciously because I've hauled myself out of the States. It's true. It's real. It's a real thing. So this American lived in the UK for a while, where he interacted directly with R.A. Fisher at the I can't remember the name of it. Do you remember the lady drinking tea, the scientist who inspired him? That's where he was working. So he got into contact with R.A. Fisher while he was in the UK, got very inspired, did some work in India. Now that's a very different place to go living, right? So India, Argentina, spent some time in Buenos Aires. Do you suppose he learned how to tango? I never did, so. All right. So this is a guy who got out of his shell and tried different things in his life, and is very much a revered figure in the space of quality control, in the space of econometrics, and certainly at the University of Chapel Hill. Okay. So, what did we learn today? When you have dozens, hundreds, or thousands of measurements that you've made for each sample, having the ability to pursue dimensionality reduction may make your science a lot easier to pursue. Principal component analysis is a classic. Loads of people use it, whether they know it or not. It appears in most statistical environments. If you're using GraphPad Prism, if you're using Perseus, whatever, you're probably going to have access to PCA along the way. A lot of times, that software will assume that you have the responsibility of understanding how it has operated. So it's best that you have a little bit of background to be able to interpret those data when they come back. PCA is most useful when you're trying to visualize the overall scatter of samples through measured space. Now, I've talked about classifiers today. I want to be careful about conflating these topics a little bit. Is PCA differentiating among classes of samples? Is it trying to figure out which aspects of the data tell two different classes apart? We've got sort of a head shake over here. Someone saying no? It does not. We do not provide PCA with class labels. We give it metrics, and it says where is the variability within these metrics. If things happen to be close to, if the cases happen to be close together and the controls happen to be together in the plot, that's great, but that is not the point of PCA. PCA is asking where is the overall variability in this data set? How can we visualize it so as to spread the data most on that variability? Hopefully the variability has something to do with your sample labels, but PCA doesn't know about that. All right? So we're going to try to work through some examples in R. I've just put together two. The document, the text file for today's lecture is in the same directory as the PDF of these slides. So we're going to go ahead and pursue that next. Are there questions before we move ahead? Okay. Hey, PCA is complex. Multidimensional thinking is not something that any of us do particularly well. That's why I want to try to walk you through this bit by bit. The figure that I think may be the most important one to understand is this one. Understanding all of the mechanisms by which this takes place is hard. So what I would ask you to do is just think about how do these data spread in my metric created space? Where is the long axis? Where is there the greatest variability? That's principal component 1 right there. Okay, so let's come back to R. I'm going to open up my R session right over here. I've already changed the font size up. Oh, I always forget that it cuts off the left edge of the screen. And bounce that over a little bit. All right. Okay. I'll just make it a little smaller. There is R. Grand. Now, I'm going to start us up to the top. I am using a library today. That is the oh my goodness, it's cropping off that edge too. So I'm going to scoot this over a little bit. All right. Scoot. Scoot. There we go. Okay. Oh, it's still showing a little off of the edge there. Bounce that over. Come on, you. Cooperate. Here we go. Okay. So we have already discussed ggplot2. ggplot2 is a great library for doing visualizations. If you're doing plotting, you can just use the base graphics of R. Sometimes ggplot2 can make things a whole lot nicer looking without a lot of effort on your part. We are using GGFortify today. So Grammar of Graphics Fortify teaches R some things about the data models created by principal components. So we're going to just use the library GGFortify. If you try to run that line and your computer says this isn't installed, you'll need to do it. So you could use the install packages command to install it, or you can just use the menu of your software to install GGFortify. It might take a couple minutes, but you'll catch up. You can see there's not a huge amount to today's examples. Now we're going to start with our iris data set right here. So I'm going to come over to R for just a moment and do a quick summary of the iris data set. Okay. So when we look at the iris data set, we see that we have 1, 2, 3, 4, 5 columns from it. We have sepal length, sepal width. Does everyone remember what a sepal is? Sepal? You guys probably have more recent agriculture experience than I do. All right, we're looking at a flower, right? So a sepal is kind of like this guarding leaf on the out. It's a specialized leaf on the outside of the flower. I'm sorry, probably all the botanists in the world just cringed as I gave that description, but think of it as like a guard petal. All right, sepal. And then we also have petals. These are the formal flower parts. Okay, we have a sepal length and a sepal width. We have a petal length and a petal width. And we have species. The species is special, isn't it? It's the factor. So species is giving us Setosa, versicolor, virginica. We have 50 of each. Those are labels. PCA doesn't eat the labels. PCA doesn't care what the labels are. It doesn't know what to do with them. So you're only going to give those fields to principal components analysis that are numeric. All right. So just as an offhand guess, does a plant with a long sepal also have a wide sepal?
Likely.
Not necessarily?
Likely, though.
Likely. Likely. I think likely is true. So it is probable that something that a sepal that is long also tends to be wide, and that a petal that is long also tends to be wide. Here's where things get really messy on the subject of correlation. Do plants with large sepals also have large petals?
Not necessary.
Not necessarily, but possible. So we may have a great deal of correlation to deal with in this data set. It could be that the plants that were most mature had the longest and widest sepals and petals, in which case all of our signals kind of in one basket. Okay, quick question?
No, I was checking way out.
Oh, we're still on the first line. We haven't gotten very far at all. Okay, so I've just run a summary of the iris data set right there. It's not even on the script. I'm just starting from there. Okay, so iris has 5 fields, but we don't want them all. We don't want the last one, which is the label, because Principal Components doesn't know what to do with that. So I am subsetting. Does everyone remember subsetting? So we're going to use these square brackets, and we're going to grab column 1, 2, 3, and 4, but not column 5. And remember, 1:4 means all the values in between as well, 1, 2, 3, and 4. So we're going to grab those 4 columns and shove that into something called iris metrics. So if we look at what happens in response to this, copying that command over. All right, so remember we did a summary on iris, and we saw all 5 of those columns come back. What happens if I do a summary of iris metrics?
4.
Just those 4. It no longer has information about the labels of species. All good. Okay, now we're going to run a principal components analysis. Is this a big data set for PCA? It's not huge. It's 150 lines. And it's 4 columns, so not terrible. Is it going to happen in an eye blink, or is it going to take an hour?
It'll be short.
It's going to be short. Computers are so bloody fast these days. So we're going to just grab that, throw it in here. It's done. Now, we got a result from the PRComp function, and there are multiple functions that'll do principal components in R. PrinComp is another one that we frequently see. Today's example is with PRComp, but they have a lot of shared principles. We captured the result of PRComp in iris_PCA. So if I just type iris_PCA, I should get back some information. And we see that we have some standard deviation that comes back and rotation information that comes back. I'm going to try to bring us back to that slide we were talking about just a moment ago. Remember we had that pile of data in the 3D space and we have a long axis on it? This rotation is describing how the new components from principal components analysis are rotated versus the original XYZ values. Okay? So if you need to understand how you're mapping from your original variables to the components that are derived from them, the answer is right here, this rotation set of values. Is the computer behaving itself? What's that? Oh, I'm so sorry. Well, if it needs to be, flapped around a bit, let me know. We'll get it. All right. So this rotational data right here is describing how the original metrics can be translated into principal components. That's the answer that came out of PCA. All right. Now, can we get a summary of that? Summary of iris PCA. Do we get different information back? We sort of do. But you see what we got back? The importance of the components. You can see that principal component 1 has a high standard deviation compared to these others that is accounted for. The proportion of overall variance, look at that, 92% popped back. The cumulative, so let me walk through this slowly. We'll pay attention to just these last 2 lines. Proportion of variance and cumulative proportion. You sometimes see R returning information like this. This was the summary of our PCA object. So the proportion of all variance accounted for by principal component 1 is already 92.46%. So just one value derived from the 4 metrics given already explains 92% of the variance. That's nuts. That's a huge degree of correlation among the metrics that we fed the software. The next component accounts for only 5% of all that variation. The third component accounts for less than 2%. So when we look at the bottom, we see that the values for principal component in proportion of variance and cumulative proportion of variance is identical. Everyone understand why? Because this cumulative proportion is counting only PC1 at this point. The next time we look at this value, though, it's risen. So this is a running sum across this next to last row. 92.46% plus 5.3% equals 97.77%. So this is the percentage each component accounts for. This is the running sum. And you see that by the time we get to the fourth component, all of the variation has been accounted for. Any questions on that? This is not graphical, but when you're writing your paper about how PCA worked in your data, pulling these numbers off is pretty useful. You can say the first component accounted for 63%, and the second component accounted for 16%. We were already over 80%, we felt good. Whatever you want. Okay, as I said, there's no hard and fast rule about how many components you should use in making sense of your data. All right, we've done our our principal components analysis. Now we're going to make a plot, the fraction of overall variance explained by each component. I want to note that I'm using an abbreviation EIGS. We are looking at something called eigenvectors. Now, some of you are really, really bright in math, and you made it through Calculus 3 in college, and you love this stuff. And so eigenvector is probably very meaningful to you. Personally, I find eigenvectors a little confusing as a topic. My friend Gerard is a much better explainer on that subject. But for now, we're going to say we do this, and out pops our variance. So let's make our little plot then of our data. Okay, and again, we see this huge gulf between component 1 and everything after that. So this is the percentage of variance needed. If you're trying to figure out how many components you must take into account in making sense of your data, a plot like this is very, very helpful to you. So we've just plotted these values from the data. But it's not different, really, than what we could have seen in the summary. Because when we ran the summary of the PR comp object that came back out, we got those numbers just the same. Okay, so how do these four metrics contribute to the components? Remember, we saw that in tabular form just a moment ago. Is that?
Yeah.
Okay. Oh, that was some other piece of something that fell off the desk. Okay. So let us return to our console window now. We're going to run this next section. We're doing an auto plot. What did I just do? Yeah, okay. We are using an automatic plot. Remember, we ran GGFortify at the head of this. That told ggplot what is the standard way to visualize a principal components object. All right, so we're doing something that shows loadings. It asks, how do we transform the data from the original metrics to the principal components? And here we've got a visualization that's comparing how each of the four values we fed to principal components fares between principal component 1 and principal component 2. If you see something pointing strongly to the right or strongly to the left here, that's to tell you that it matters profoundly in how something is weighted in principal component 1. Why do you need to know this? Because when you show a principal components graph in one of your talks, someone is going to ask, how do the components map to? What relationship do they have to the values you fed principal component analysis? It's a very obvious question for someone to ask. Fine, it separates on a PC graph in principal components, but what does it mean? When you're trying to interpret that, a graph like this is very helpful, because here we see that petal length and petal width are the main drivers in separating the data in principal component 1. The second component starts making use of this sepal length and width. That's why it has an arrow pointing out from the origin. All right, so that was produced by this auto plot, and you can see that I've done loadings equals true, loadings label equals true. That's why we got that red flower in the middle of the data set. But now let's look at the ggplot graph, this time leaving the loadings off and using coloring on the basis of species. Now remember, principal components analysis did not receive those class labels. Here we're bringing those in from having left them behind earlier. We're going to add those in to a principal component analysis that did not receive that information. Did we find that our class labels really did separate on the basis of the underlying variability in the data set? Oh, come back here. Paste that in. Okay. Now we have our data. So we have the same principal component 1 and component 2 right here. And we see that our data, our classes, Setosa, Versicolor, Virginica, although they were not provided to PCA, are separated pretty well when we look at the principal components derived from those data. We see that Setosa is at a much lower principal component 1 score. What were the metrics that contributed the most to principal component 1? We saw it in the graph just a moment ago. What were the red arrows pointing to the right? Petal width and petal length. Both of them. So taken together, we see that these Setosas are almost always getting very negative principal component 1 scores, which is to say they have short petals by comparison to the others. If they separate out on the principal component 2 axis, then it's probably making a statement about the sepals. All right? So interpretability is key in principal component graphs. I want you to be armed when you have to deal with making sense of these things. So that's why I'm going through this elaboration. Now, would we say that Versicolor and Virginica are easily separated on the basis of the principal components derived from these data? Not great. Not great. We could throw a diagonal through here, maybe right there, and it's going to make some errors. But we could make a classifier based on the principal components that might or might not be better than it would be on the data we fed principal components. Okay, so that is our interpretation of our principal components graph. That was the end of the first demo there. But you know that this statistics class that we're doing is a little unusual in that we tend to do a lot of simulated data. Now I'm going to walk you through this next example. It's already noon now, so I'm going to have to do it short again, but we're creating 2 random variables, uniformly distributed, A and B. But we are not going to provide A and B to principal components analysis. That's the tricky part. Instead, A and B are hidden variables. They just sort of manipulate things from behind the scenes. So A and B are produced in the first place. We then generate a metric 2 and 3 that take the values of A and B into account, but not perfectly. We either multiply the value of A by 1 or by the value of 3. We either multiply B by -3 or -1. And in both cases, we add random noise on top of that. Okay? So metric 2 and metric 3 take A and B values into account. Both of them take both into account. But metric 1 and 4 are just random numbers. Okay? We're not going to provide A and B to the principal components analysis. Instead, we're going to make a new metrics table that combines metric 1, 2, 3, and 4. So what are the 2 metrics that can give principal components analysis some idea of the contribution of A and B? 2 and 3, right. Okay, so we haven't listed them first, we just put them, shoved them right there in the middle. Is principal component analysis clever enough to figure out that metric 2 and 3 have something to do with each other? All right. So let us go ahead and run our simulation. These are random, so your results may differ slightly from what I've got. All right. So I'm going to do a summary of Sim PCA. All right. So, principal component analysis, principal component 1, is capable of explaining 42% of overall variability. The combination of principal components 1 and 2 accounts for 2/3 of the variability. So we're seeing a bigger drop-off on 3 and 4 behind that. We can visualize those. I've included that code right here. It's just the same as it was before. If I glom that in there, we see that principal components 1 and 2 account for considerably more of the variation than do 3 and 4. Nothing so remarkable there. Now, which metrics are most heavily weighted in these components? Okay. There it is. So we're doing that graph again, where we show which factors are most useful in determining the value of the underlying relationships. And we see that metric 1 and metric 4 are right here in the middle. What does that mean? Metric 1 and metric 4 in the middle, are they contributing to computing the value of principal component 1 or 2? Not at all. Not at all. So we see that metric 2 and 3 both contribute. They're both to the right. They both have a substantial horizontal displacement. That means that they both figure into computing the value of principal component 1, and they also have a vertical displacement, which means that they're also used in computing the value of component 2. So in effect, principal components analysis from these thousand rows is able to decide that both metrics 2 and 3 can be used to infer 2 different sources of variability underlying it all. So even though we didn't provide A and B to principal components analysis, by being hidden inside metrics 2 and 3, it was still able to discover that there were 2 factors at play in separating these data points. I think that's pretty cool. Okay, that's it for today. We are back here next week, where I believe we're going to talk about multiple testing comparison, a subject near and dear to my heart. But in the meanwhile, thank you for coming back, and I look forward to talking to you next week. Thank you, everybody.
Thank you.
Yes, perfect.